What we're going to do in this video is get some practice identifying what is and isn't a mathematical proposition. And then we're going to think about how we can join those propositions together using logical connectives. Now, before I even start defining things, I have a few sentences written here on our digital board, and I encourage you to pause the video and see if you can point out which of these you can actually assign a truth value to. Meaning, can you say if it's definitely true or definitely false?
All right, now let's think about this together. A proposition, or a statement, is really just a declarative sentence that is either true or false, but not both. So, looking at our list, if I have the sentence, 37 is a prime number, that's clearly true, so that's a proposition. If I have a triangle has 4 sides, that is definitely false, which actually still makes it a proposition. Remember, a statement doesn't have to be true to be considered as a proposition. It must be either true or false. But what about close the door or what is your name? These are commands or questions. They don't assert that something is the case. So my brain likes to think about these as non-propositions because they don't have a truth value. Even if we don't immediately know the truth value, like a sentence about the 1000th digit of pi, it's still a proposition as long as it could be asserted or denied. Meaning, once we found out the 1000th digit of pi, if it is indeed 4, then the statement will be true. But if it is not indeed 4, then the statement will be false. But either ways, the statement is a proposition. Now, once we have these building blocks, we can modify them or join them using what we call logical connectives, such as not, and, or, implies, and bi-implies.
The most basic logical operation is negation, which we usually denote with the symbol tilde. If our proposition P is 27 is a composite number, which is true, since composite numbers have more than 2 factors, and 27 has factors such as 1, 3, 9, 27, then the negation not P is simply 27 is not a composite number, which is false. Negation just flips the truth value. Note that the phrase not a composite number is not necessarily equivalent to a prime number, since a number can be neither prime nor composite, for example, 1. Therefore, the statement for not P remains 27 is not a composite number, with a truth value of false. Next, let's look at joining two propositions. When we use the word and, we call it a conjunction, denoted by the inverted V symbol. For a conjunction to be true, both parts must be true. For example, consider the statement 3 is an odd number and 27 is a prime number. Let's evaluate it. 3 is odd, true, but 27 is not prime, false. Because the second part is false, the entire conjunction is false. Now, let's look at the possible combinations of truth values for two propositions joined by a conjunction in a truth table. As shown in the table, a conjunction is true only when both propositions are true. Otherwise, it is false. Now, this should be fun. Let's look at OR, which we call a disjunction, denoted by the symbol V. In logic, OR is usually inclusive. This is a bit different from how we talk in real life. If someone says they will go to a football match or the cinema, they usually mean one or the other, where if one goes to one of the places, the statement will be considered true. In somewhat similar manner in math logic, a disjunction is only false if both parts are false. So 3 is an odd number or 27 is a prime number is actually true because the first part is true. Now, let's look at the possible combinations of truth values for two propositions joined by a conjunction in a truth table. As shown in the table, a disjunction is false only when both propositions are false. Otherwise, it is true. The last two are really important for higher math. We have the implication, or the if-then statement. For example, if 3 is an odd number, then 27 is a prime number. We call the if part the hypothesis and the then part the conclusion. An implication is only false in one specific scenario, when a true hypothesis leads to a false conclusion. In our example, the hypothesis is true, but the conclusion is false. Therefore, the entire statement is false. Interestingly, if the hypothesis is false, the whole statement is considered true by default. However, if the hypothesis is true, the conclusion must also be true for the entire statement to be true. Finally, we have the bi-implication, or if and only if statement. This is only true when both parts have the exact same truth value. Either they are both true or they are both false. Let's take an example in both scenarios. First we have 3 is an odd number if and only if 27 is not a prime number. In this case, both the propositions are true. As a result, the statement is true. On the other case, 3 is not an odd number if and only if 27 is a prime number. In this case, both propositions are false. Therefore, the statement is true, since the propositions have the same truth value. Here, we can summarize both connectives in the truth table. As shown on the table, implication is only false when the hypothesis is true and the conclusion is false, and bi-implication is only false when the propositions have different truth value. And we're done! Hopefully that makes some sense and gives you a good feel for the basic language of logic. If this was helpful, go ahead and hit that subscribe button to join our community, and I'll see you in the next video where we'll start building compound proposition and their truth table. Thank you for watching, and see ya!